Good afternoon, good evening, uh, good morning to everybody who has joined in today. So it has been a good exercise for Objectify Technologies um, to to talk about the AM technology through these webinars. So we started this activity on April 6th, and today is August 6th again. So it has been good 4 months of this activity where we had tried to incorporate about the technology. We had been talking about the application of the technology. We have got eminent speakers, eminent panelists who had joined us from different organizations around the globe. And so today we'll be finalizing our new series of 4 webinars which we did. Um, so it has been a great pleasure. So I am Ankit Sahu. I'm the co-founder and director of Objectify Technologies, and I really thank you all for joining in for this session and making it a great success. And I've been getting a lot of emails, a lot of WhatsApp messages, and a lot of LinkedIn requests on our initiative on these webinars. So it has been a great journey through these webinars, and I would like to thank Mr. Sankar Shubra Deb, Mr. Ashish Jacob, Mr. Rahul Pise, Mr. Brigu Ahuja, and Mr. Nishant Kashyap. And along with that, I would like to thank Mr. Arpit Sahu for making these webinars such a great success. And it has been a great pleasure talking to you guys and explaining about the technologies. And I think with these 4 months of hard work from our team, it would have been gone really well with the audience, and it would have changed the mindset, and it would in turn make you more ready for adoption of this technology, which is a wonderful technology because it crosses all the verticals, all the horizontals of whatever you require in a manufacturing setup itself. So today we'll be concluding our series by talking about aerospace, space, and defense application of AM additive manufacturing itself. So as I've already mentioned to you that we have been talking about broader topics like how to be an informed AM buyer, because people, they know about additive manufacturing, but they don't know what are the criteria required for being a good additive manufacturing buyer itself. Then we talked about a lot of pre and the post processing, as people have been misunderstood about the technology, that you just go to a machine and it will directly make a component which is directly easy to use. So we wanted to decipher that, and we talked more about the pre-processing of the data to the post-processing, the whole project management requirement itself about additive manufacturing itself. And then we last week what we did was AM materials, so additive manufacturing materials from the polymer side, from the metal side, how to characterize them, how to develop them for additive manufacturing use, and how to test and report them, and what are the properties you require, what are the things you require according to your end application itself. So that has been a journey, and I think it was very well appreciated between all the users. It was very well taken by the students, and it has been a great honor to conclude this with this topic, which has been talk about AM, and it is a top-down approach for AM itself. And these have been like the early adopters and technology drivers for additive manufacturing. So we will be talking about aerospace applications, space applications, defense applications of additive manufacturing. And today your presenter will be Mr. Arpit Sahu. Um, he is the co-founder and director of Objectify Technologies, and he's my brother. And we work together and manage this company. And we really welcome you all for this webinar. Thank you so much. So so there'll be some polls also, and you can post your questions for the panelists, for us, on the questions Q&A section, and we will be happy to answer all your questions itself. So over to you, Arpit. You can go ahead.
Thank you, Ankit. Thank you for explaining in detail. So welcome everyone to today's webinar session. We have been running these webinar series since March, and this is the final of the lot. I would like to thank everyone for joining in today from all across the globe. You are in for a great informative session on aerospace, space, and defense applications of AM, as we will be joined by dignitaries from all spheres of the industry and take in your queries, and we'll try to answer them to the best of our ability. So let's begin with the aerospace, space, and defense applications in webinar. So here is a small recap of the previous webinar that we did on AM materials characterization, development, and testing. So we had talked in detail about the different polymer powders, polymer materials available, different metal materials available, different post-processing, characterization, and testing. So we had an eminent panel of Mr. Dilip Menzies from 3D Systems India, Professor Deepankar Banerjee from Institute of Sciences, Dr. Kumar Kandaswamy from Enabled Engineering, and it was taken care by our CTO, Mr. Brigu Ahuja. So the panel for today is Dr. Donald Godfrey, who is a senior fellow aerospace and defense additive strategy at SLM Solutions, USA. Dr. Govind Bajargan, Syrian scientist from Vikram Sarabhai Space Center, Indian Space Research Organization, Trivandrum. Mr. Prakasam Anand, country head, US GmbH, India. And me, Arpit Sahu, co-founder and director of Additive. So whenever somebody talks about the application of AM in defense, aerospace, and space sectors, they talk about what are the ideal requirements for design and manufacturing in these sectors. So generally, the first thing comes to anyone's mind is complex designs are required for better functionality in these sectors. So just like you require low weight to increase the payload capacity of a missile or a space rocket, you need very complex designs for high fidelity controls over engines and other mission critical parts. In civil aviation, you require better design to have better fuel savings. And secondly, the applications here are inherently risky and expensive. Therefore, designers try to reduce the possible failures as much as possible. So they try to have the least number of joints, least number of fasteners, and try to design a more seamless part. They go for very tight tolerances in these applications, and they try to go for the best materials available with high properties and good functionality. And these sectors are also characterized by low volume and customized product requirement. So in this case, we try to answer this question, why to go for AM in these sectors? First thing is the design freedom for complex designs that AM offers. Just like it offers good topology optimization, which can result in weight reduction and manufacturing of previously impossible designs to increase the performance. It can result into part consolidation, thus reducing the chances of failures. It also saves time for doing big complex assemblies. And one thing that is very integrated is that the design readiness for an AM part is much faster compared to a conventional manufacturing process. It is ideal for small batch and customized production because you don't require any toolings. The turnaround time is pretty quick, and there are a lot of cost savings in it. And it is very good for this sector, especially for the rapidly and continuously evolving designs, because you don't have those millions of parts in production that is required. The supply chain is also relatively short in this technology. You have less manpower requirement as most of the things are automated. You end up having more material savings. You can even opt for on-site production and end up saving the environment. And specifically, you have a lot of high-end materials that are available in AM for the desired applications. So let's try to discuss the various applications through actual cases. So the first thing I'm talking about is topology optimization resulting into weight reduction. So you can see this part. This part is a VTM bracket part in SS316 alloy for space application. So this part has been designed specifically for AM, and you can see the topology was optimized using the load conditions. So the weight was reduced from 7.48 kgs to 3.5 kgs, which is a very significant weight reduction of 52.4%, resulting into better payload capacities in the rocket in which it is fitted. The second part is topology optimization and manufacturing designs we were previously thought to be impossible. This is an example of a high pressure turbine blade in Inconel 718 material for engine application in aerospace sector. So you can see the complete build of this blade printed in AM with small 1.5 mm dia cooling channels. You can see the small holes which are there, so they go through and through. This allows for better cooling of these blades and better aerodynamical structure as well, resulting in better efficiency of the engine on which these blades are operating. Then we see one more application of part consolidation in avoiding joints which can result into a failure. So this is a case of air bottle assembly in titanium 6 for alloy. This is for a specific defense sector requirement. So you can see this is a completely hollow donut shaped geometry, and generally traditionally it has been manufactured through welding route by welding the top and the bottom, which results into a seam, which uh, increases the chances of failures in terms of high pressure situations. So here we are trying to avoid that, so resulting in better functionality. And one more example of part consolidation resulting in saving time for complex assemblies. So here we are taking an example of a flame tube part in Inconel Sec 5 material. For aerospace engine application, you can see the part can be manufactured through assembling a lot of sheet metal parts, which may result into a lot of fixtures, a lot of complex assemblies. But here in AM, we can manufacture this part in a single shot, and this is an AM manufactured part. So it avoids any failure points. The complex assembly time is saved. It also improves the performance and reduces the supply chain. So the main motivation while redesigning the part is the functional integration, resulting in the structure optimization, resulting in a very good redesign structure. So this process and the design approach is very frequently coming to use in 3D printed rocket engines. You can see few pictures where all the parts are integrated into one and trying to increase the performance of the systems. Then we are looking at faster manufacturing readiness for design in AM. So here we are using a detonator part in nylon glass filled polymer material for a defense application. So this part, you have to redesign it a lot to avoid undercuts and to make it feasible for manufacturing in processes like injection molding. But AM has a lot of advantages over processes like injection molding and die casting. Here, the designer doesn't have to take care about the undercut feasibility requirements, don't have to think about the parting lines, injection marks. The sole focus of the designer here is on the functionality of the part rather than the feasibility of the part. So, resulting into a much more optimized and better design. And AM is a very good medium for small batch and customized production. So we can see in AM you don't require any tools and the turnaround time is pretty quick. So we are taking again a defense part. Uh, this is a duct part in nylon glass filled polymer material for a defense application. So this part was delivered just in 3 working days to the end user through additive manufacturing route. Conventionally, this part is manufactured through blow molding route, for which the tool itself would take at least 2 months to develop, and the tool cost would be very expensive in this case. So AM provides a very fast and quick solution in this case. And specifically, these space, aerospace, and defense sectors have continuous evolving design. It is not like automotive sector, where once you design a system and you at least make maybe 100,000 copies or 200,000 copies before changing it to the next generation system. But in AM and in defense sectors, you may change the design after just 2 copies and try to improve and have the experiences put into the new design. So AM is a pretty good medium for that. So you don't have to invest in the tools, and you can quickly evolve the design as you want. AM also results into shorter supply chain. So in any conventional manufacturing process, uh, you have to use a lot of raw materials, different suppliers, a lot of different parts are manufactured at different points and then assembled together and then given to the end user or the consumer. But in AM, once the designer designs the parts, the input is directly given to a 3D printer or a printing machine, and directly the parts come out, and it is given to the end user or the consumer. So it reduces the supply chain and even allows for on-site production. So the advantages are lesser manpower, leaner infrastructure, and possibilities of on-site production, and a lot of material savings as well. And as in these sectors, the designs are mostly critical, so people also don't want to share the design to a lot of stakeholders. They also want to keep the design within maybe just one or two manufacturers or vendors. The other advantage is availability of a lot of high-end materials in AM. If you look at the polymer materials that are available in AM, you have materials with high strength, high good transparency, water resistance, temperature resistance, high resolution, durability, stiffness, and impact resistance. You have good variations of glass-filled materials with reinforced uh, plastics. You have Acura 60, which is very transparent, Somos Evolve. You have even flame retardant materials for critical applications. So you have a lot of options in AM material wise to manufacture the end part. In metals as well, you have a lot of options, and a lot of these materials are used for end use parts. So you have good materials in terms of strength, temperature resistance, corrosion resistance, high strength to weight ratio, toolings, refractory alloys, casting alloys, super alloys, biocompatible materials, conductive alloys. So you have Inconel based super alloys which work at high pressure and temperature conditions. You have different steels. You have titanium you can use for weight reduction applications. You have tungsten. You have copper for critical conductive applications. So you have a big bouquet of materials available in AM. And for critical specific applications, you can even go further and develop new materials for those applications in AM. So now the question comes, why AM is pushed uh, a lot for production in these sectors, in space, aerospace, and defense applications, why they are considered to be very critical for the AM technology. So I'll explain this using two cases. So the first case, I would be comparing die casting versus additive manufacturing. So you can see this aluminum casting, it is apart from the automotive sector in aluminum alloy. So the general requirement in automotive sector and this part is around 300,000 pieces. And the single AM part costs around 700 to 800 US dollars. But if we go for the die casting route, which is the actual production route for these end use parts, the tool cost itself is 80,000 USD, and the eventual part cost is just 10 to 12 USD. And you can see when you have such a huge 300,000 pieces requirement, the tool cost is amortized. It is not even half a dollar per piece. So for commercially, for very high volume automotive type requirements, the AM cost would be very high uh, for end use. But for low volume requirement, just like in aerospace and defense sector, where you have just a requirement of 50 pieces or 100 pieces, then you won't be able to amortize the tool cost. Then AM comes into picture and it can manufacture the end use parts. The other example I would be taking for a part, comparing block machining versus additive manufacturing. So this is an end fitting part. This is a space sector part in titanium alloy. So it is required just around 10 pieces for actual usage. The AM part costs around 900 to 1000 USD, but the CNC machining part would cost around 1600 to 1800 USD. In this case, the AM part cost is lower because the expensive cost of titanium block required for subtractive manufacturing is pretty high. And machining materials like titanium or Inconel is very slow and tedious. And the cutting tools for machining these materials are expensive as well. And even if you're going for AM, you can redesign the part in a much better functionality. So in this case, AM going for AM makes perfect sense. So the low volume and the customized requirement makes a very good case for AM in these sectors. So like any other technology in any industry has few challenges as well. So AM has currently these challenges. So a lot of industry specific qualification standards are required, which are still being codified. And then replacement of pre-qualified parts, because in these sectors, a part takes around 3 to 5 years to qualify. So maybe an organization doesn't want to invest in a new technology to qualify a part. Then obviously in AM, we still have part size limitations. It is very good for manufacturing parts around less than 1 meter, but parts bigger than that, obviously there are cost and build volume limitations. And obviously, in terms of scaling of production, when compared to conventional process like molding, it is easier in scaling of production in molding. And a lot of times for these applications, you require very specific and exotic materials. So every time you have to move ahead and develop that material here. And obviously, are some post-processing challenges as well, like any other technology. So with these challenges, I think we would go towards our survey and take the feedback from our attendees, what they think about AM and AM specific questions. Sanka, over to you.
Yes, I'll be launching the poll right now. I would request everyone to kindly give in your responses of what you think will be the correct option for this. The polls will be 3 polls back to back. I would request everyone to please give in your votes. So the poll is running. Meanwhile, you can also give in your questions in the question section so that our panelists as well as us, we can answer accordingly to your queries. So please give in your questions as well. Sir, over to you. The poll is running currently. I'll be running one poll after the other.
So we would be, thank you, Sanka. Thank you. So we would then move towards our panelists for today, Dr. Godfrey, Dr. Govind Bhajarkan, and Mr. Prakasam Anand. So as soon as the poll closes, we'll start engaging them with them one-to-one, starting with Donald Godfrey.
I would request everyone to please give in your responses so that we can move forward with the presentation. Thank you so much.
We'll be taking up the perspective of the panelists on different game-specific questions and try to understand and learn from their views on the topics that they will be discussing. Hopefully,
So the final poll is on your screen. This is the last poll.
we'll be sharing and discussing the poll results at the end of our panelist talk, and we'll go through the perspective of the attendees in detail after that.
Yes, sir. The polling is over. You can go ahead.
Okay. So we'll be starting with Dr. Don Godfrey. So Dr. Don Godfrey is a senior fellow aerospace and defense strategy at SLM Solutions USA. Dr. Godfrey is a globally recognized authority on additive manufacturing. For Honeywell Corporation, he opened 3D printing labs in China, Czech Republic, India, Mexico, and 3D printing facilities in Phoenix, Arizona, with 2 being production facility. He's also an author of the book Additive Manufacturing of Metals, the Technology, Materials, Design, and Production, Springer Series in Advanced Manufacturing. Dr. Godfrey is also the recipient of 30 plus patents in the US and similar number in the EU. Dr. Godfrey has spent the past 3 years in developing the additive global supply chain. I would request Dr. Godfrey to put forward his thoughts on the following topics. Over to you, Dr. Godfrey.
Thank you. What I'm trying to convey in this slide is that even though additive manufacturing is a phenomenal science, culture and the perception of risk is our greatest hurdle. For organizations not familiar with the science of additive manufacturing, you have to convince them that changing from an existing production that of a component that might today be sheet metal or castings or forgings to an additive technology is not risk. They see it as risk. So, for example, you have a difficulty getting a part, or you have to reduce the cost of something, and you want to use additive manufacturing. It is a typical response from an engineering organization to come back and say, hey, delivery issues, cost issues is a supply chain problem, not necessarily an engineering problem. When you want to reduce weight, that is an engineering goal, and they might be considering use of additive. But when there are large organizations, if you can pick any aerospace OEM, and they have within their organizations groups of people whose job it is to reduce risk. And so you have to convince them to change from a casting to a printed part. When you make that change, you're inducing risk. So how do you convince them to do that? Well, one way is through convincing engineers, chiefs, and even the customers, the FAA, ESA, that your additive manufacturing process is governed by specifications, powder specifications, ASME specifications, MMPDS. There's a lot of work that has to be done after you've developed the printing process. And the FAA has a pretty standard process or a belief that you have to prove that your additive manufactured part is as good as or better than what's in production today. They're not going to just let you go out and change a qualified part. If you're talking about a part that's on a new engine, a new design, and you 3D print it, okay, that's great. And they'll qualify the engine, and if it works, fantastic. But if you're talking about replacing a part that has been in production for 10 to 20 years and you want to now make it additive, you are in essence changing the manufacturing process, and by default you are inducing risk, and you have to prove to them that the risk isn't there. And that's why I say culture and perception of risk is the greatest hurdle. We need to do the science to prove to the FAA and ESA that risk is not increased. To give you an example, there are aerospace companies that, one in particular, that over the past 2 years have had tragedies occur to their product line. I can guarantee you they have zero interest in doing something that might increase risk to their product. And we at in the United States, to get something approved, you have to go through a complete material characterization of the alloy through additive. That's what I'm trying to say here, is that you have to prove to people that additive is not a risk.
Thank you, Dr. Godfrey, for your very illuminating talk and perspective on having additive into a conventional process and reducing the perception that AM technology is not a risk, but a tool for making better products.
You're welcome.
Thank you. So our next panelist is Dr. Govind Bhajarkan. Welcome, sir. He's a senior scientist at Vikram Sarabhai Space Center, Indian Space Research Organization. He has illustrious educational qualification background. He has done a bachelor's in metallurgical engineering from MNIT Jaipur and MTech from IIT Kanpur, and he has done his PhD in fuels engineering from IIC Bangalore. He has been working at VSSC ISRO for the past 25 years. His areas of interest are physical and mechanical metallurgy, solidification and casting, and additive manufacturing of aerospace components. Dr. Govind, I would request you to share your thoughts on the following topics.
Thank you, Apit. As Dr. Godfrey said, that additive manufacturing in space has a huge potential, but right now there is a cautious approach, and components which are being identified for AM and are being printed through additive manufacturing are being evaluated thoroughly, and the process has huge capability. As you know, that complex components can be easily printed. Equally there, even because it's a repeated welding process as we look into the science. So the fine defects, catching those defects and then giving a feedback to the process, to the parameters, optimizing the parameters are really challenge. So in situ monitoring, putting sensors in the builds are really what can improve the reliability of the process. Is one of the aspects really we are looking for. As we change for identifying a component for AM instead of conventional processing, when we go for it, the major points what we look for is that the conventional process is having some problems, some difficulties, or there are huge rejections. There are some uncertainties that this process, the conventional process, the component process through conventional route can give a problems later. So those components are easily identifiable. Like we have, many components have been, rocket parts have been printed through AM and have given very satisfactory results. Turbopump parts like impeller casings, we are looking for, we are identifying these components for AM because they are complex. The process of realization is really huge, like machining, brazing, all these processes are involved in that. Through AM, in one shot we can get it. Integral component we can get it. So these are advantages we are looking in AM. not only complex. Now propellant tanks are being printed through AM, where the gain is in mass, like material saving is there, time saving is there. So overall cost reduction is there. Spacecraft components, the topology optimization is there, which leads to weight saving, and weight saving in spacecraft is a huge gain in aerospace. Fuel injectors, where each injector elements were brazed in the main body and whole component is made through conventional route. By AM, now design itself is being modified and whole assembly is made integrally. So this process improves the reliability in these aspects. So many of the components where brazing, welding, these are involved, they are good candidate for switching over to AM. And it is being done also, but approach is cautious because any process change in aerospace requires exhaustive characterization, exhaustive qualification. So it is being done, and I'm happy to see very positive results in these areas. Coming to design part, AM is really playing a good role there. Many complex assemblies can be simplified. Many parts from the assembly, now assemblies are being made as a single integral component, or even 75% or 80% of the components are made into one. This is another aspect of AM where aerospace is interested in, and is really, AM is being utilized for that. We have seen it in nozzles, we have seen it many other hardwares. Thrust chambers, where helical coils are machined on the surface and then it is joined with another metal. Now AM is able to give integral thrust chamber, and which has been successfully tested also. So these are really amazing applications where AM can find and simplify aerospace manufacturing. Qualification is really an important aspects for aerospace. And here I feel and I strongly believe that AM can come up with in situ monitoring of the process. In situ sensors can be used, which can give a real-time data, so that post-qualification efforts can be minimized. Because when component is complex, that qualification or entity part is equally difficult. So for qualification, very few standards are there, and we find that AWS D20 is giving a good guideline. Here the idea is that the machine is calibrated. First concept which comes is the machine qualification, where the machine is calibrated, but then the build volume, the machine is able to deliver the desired parameters precisely, or there is a deviation. If there is a deviation, then how it is going to affect the print. So this is the concept what AWS D20 uses, and that builds up a confidence in the process. So qualification, when we divide into 4 different categories, like powder qualification, powder characterization, process parameter optimization, pre-production qualification, production qualification. So there are a lot of elaborate things in qualification. And as far as whatever printing we have done, results are really encouraging. And I really strongly believe that AM will definitely change the aerospace manufacturing. Thank you, Arpit.
Thank you so much, Dr. Govind, for explaining in detail what type of parts are you looking forward to manufacture through AM, and what are the challenges that you are facing. So it was a very, very illuminating on this particular topic. Next, I would welcome Mr. Prakasam Anand, Country Head, US GmbH India. Mr. Anand is a pioneer and an avid promoter of AM. As the country head of EOS India, he is in the works to increase preparedness for the next generation of design thinkers who inspire to aspire and achieve the impossible. a true believer in additive manufacturing, which can change the face of many industry segments in the near future. He believes that EOS as a catalyst in enabling that transformation in India. I would request Mr. Anand to share his thoughts on the following topics.
Thank you, Arpit, and thank you, Objectify Management, for inviting me for this session. Well, my experience would be based on the work which I have done closely with agencies like HAL, GTRE, Indian Air Force, Rolls-Royce, SAC, and LPSE. So, based on those experiences, I would like to share some of the key points from a advantage point of what additive brings to the table. So I'd rather start with the last point, value engineering. Uh, from my perspective, I've seen that most of the aerospace or defense customers have looked into AM to create a certain value. I mean, without a value, why should you change the manufacturing process? So the value starts from the design. So the design, again, you don't think too much onto the manufacturing constraints or the processes, but you start with the design and try to find what's the value you can deliver, be it weight reduction, topology optimization, whatever you call them. And so once your design, you're able to create a certain value, then I think you have a better sort of a value proposal to use this technology. If you look into the negatives, or you can say the challenges of manufacturing process, well, casting also has challenges. Casting has porosity, but so many casted parts are flying. Why? Because we have enough data, we are able to fine tune these processes, and we believe in them. So one of the important thing is to believe that we are able to provide the fine-tuned, production process for additive manufacturing. And when you create a value in your design and then take it into the manufacturing process, I think this is the first biggest step. Then I always would like to focus on the asset flexibility, because as you see, we are now living in a world where there is a lot of uncertainty. So when we talk about asset flexibility, gone are the days, or probably it will keep changing. The large brick and mortar companies would probably focus more into distributed manufacturing, because you want to be closer to the consumers and you want to be able to support things. So additive manufacturing, when we talk about asset flexibility, you need less infrastructure, less number of operations, and also it's an agile manufacturing process. I mean, what do I mean by that? In a single hardware or a system, you're able to at one time build a part for let's say a turbocharger, maybe a medical part, maybe a part from another automotive industry. So you have a sort of agility and the flexibility to sort of use this machine for different aspects of production. So from a concept of distributed manufacturing and from a concept of asset flexibility, there is no better manufacturing process in the world which currently offers this advantage. So I strongly believe that, when Dr. Donald Godfrey mentioned, that you have to convince the people the risks are minimal. So, or we are able to mitigate the risks. So I think once that statement is addressed, then people are able to see the value which this technology is able to provide, and the asset flexibility, which it's able to bring to the complete supply chain. Then the another point I want to focus especially to the aerospace community, space community, is the buy to fly ratio. With additive, I think the buy to fly ratio is very high. There was a study which was done with Airbus, where a certain part was taken and compared along with investment casting and powder bed fusion printing. it was a titanium part. So the buy to fly ratio from the powder bed fusion was 1:1.2 to 1.3, whereas the investment casted part ratio was about 2.1. So typically it also saves a lot of energy and all these things. So the buy to fly ratio, especially, it's a big benefit for the aerospace community. And the last point, which I also would like to emphasize, is on the costs, because costs are always discussed. Once people are understanding the value the technology can provide, then typically the next point is always the price. So always today, there's a lot of misunderstanding of calculating cost, because people compare manufacturing cost to manufacturing cost. So typically, what we always advise people is to look at the complete life cycle cost, because we are talking about from the drawing to the end of life of the product. So drawing to end of life, not drawing to part, but drawing to the end of life. If you look from there, I'm sure the benefits of additive, especially in this aerospace domain, cannot be missed out. And definitely we're talking about right from raw material, transportation, manufacturing, operation, end of life. So if you go by that sequence, there's a lot of impact on energy, carbon dioxide emissions, materials, waste. So when you look into all these things, not only for the individual companies, but also for the society in large, additive can change the way things are manufactured and can make our life much better. So with this short overview, thank you very much.
Uh, Thank you, Mr. Anand, for taking us through a very detailed life cycle benefit of AM rather than just the part-to-part benefit. Thank you so much for the thought on this particular topic.
Thank you.
So now uh, we have few questions to our panelists that we want to discuss, starting with Dr. Godfrey. Dr. Godfrey, you being a veteran in civil aviation AM components, we would like to understand what are the potential percentage of parts that you estimate will be converted to AM from the civil aviation sector. Hello.
Hello? I think you can hear me now. Um, you asked what are the
What are the
what are the
potential
yeah
percentage?
what are the potential percentage of parts that you estimate will be converted to AM in the civil aviation sector?
Yes.
Um, that's to answer that with some degree of accuracy. I think we have to look at the civil aviation sector as a piece of pie. You have newer you have newer planes, planes that are 20 years old or less. You have planes that are 20 to 50 years of age. Right? I just put a part in production that was designed in 1959. And then you have the emerging market. So let's do the easy one, the emerging market. I think there's going to be an explosion in UAVs and drones, led by companies like Uber, Amazon, FedEx, DHL, and they're small, right? Every one of those things are they're not a jet. They're designed to carry a box or up to 4 people. I think all of those components, all of them can be 3D printed because of their size. Now, that's not going to happen in 2021, but by 2050, I think we can say with some level of confidence that a vast majority of those parts can be printed because the turbine engines are going to be small. They will fit in a machine. There's not going to be one big one. There's going to be 4 or 8 small ones. If they're electric, then obviously you're not going to print them. Well, you could print maybe some elements of the motor. So I was working a lot with Bangalore, India, on some power generation rotating components. So they could print some generators. We still have to get over that hurdle of rotating parts and understanding creep properties. So we could talk about that all day. So let me go into the next section, which is the aviation components that are in production today. I think from a interior of the aircraft, obviously lots of parts can be printed. If you went to Boeing Seattle plant right now, they have polymer machines sitting on the production floor printing parts. I was over at the Boeing defense helicopter plant in Mesa, Arizona, and they've got SLS machines printing plastic components right there. So it's happening today in aviation, in commercial aviation, for helicopters and aircraft interior. But again, those are the planes that are most concerned by the OEMs with risk. So we are printing some engine components, but that number is less than 1%. So if you look at it from a positive perspective, the industry is going to explode as OEMs, airframers, and engine OEMs gain more confidence. So it'll never be 50%, but it could be 5 to 10 on the outside. If you look at really old aircraft, right? The answer there is very high, because you don't look at unit cost. We are engineers and we like to think that if a casting is $20, I got to print something for $20 or I can't compete. And what I try to tell people is don't always look at unit cost. Look at working capital. So for example, and here's a perfect example is I'm at Tinker Air Force Base, which is a repair overhaul facility. And a gentleman says to me, I've got $3 billion worth of aircraft I can't fly because each one of them has a part I can't get. All right. So if you have a part where the casting is normally $500 and you print it for $1,000, is that a good investment? Because with that $1,000 part, I can now get that $20 million aircraft in the air. What are you willing to pay to get that jet in the air? Another example is if we had this problem all the time. If you need 60 castings a month and your casting house shorts you 10 and they do that repeatedly, But that casting, I think it was like $250. But when you don't ship, if you don't have that part, you don't ship that engine. If you don't ship that engine, then your customer fines you $10,000 a day or $20,000 a day. Now all of a sudden, that $250 part costs you $250 plus $200,000 because you were late shipping the engine. Because if you can't ship the engine, they're not shipping the plane. And so you need to look at working capital. The cost of that casting is not $250. It is $250 plus the lost revenue of not shipping the engine plus the fines your customer is going to give you every day that you're late. That's the cost. That is what we call working capital. So if you look at older engines and older aircraft, I think the number can be 40%. It can be way up there, but you have to give them confidence that it's as good as what they expect. Okay.
Thank you,
So,
Dr. Godfrey,
you're welcome.
giving such a detailed outlook about the pros and cons of AM parts, how to get AM parts in civil aviation. So now I have a question to Dr. Govind. You being already screening a lot of parts to convert from conventional manufacturing technologies to AM, I would like to ask you that what are the factors that are considered during part screening to qualify a part to convert to additive manufacturing production?
Yeah, Arpit, this is interesting. See, when we started AM was more like a new process and we were getting acquainted with the process. Now, the criteria what we are adopting is, first we look for the complexity. Part is complex and the route it is being made, suppose it is casting or it is machining from a big block where multiple settings are there. And a lot of material wastage is there. Lead time is more. So we go for selecting such parts. In addition to that, we have to look for the size of the part, whether it is printable in the country, whether the material which are available for AM printing can meet our design requirements. If all these things are okay, then we go for surface finish. If there is any specific surface finish requirements are there, if they are meeting, then definitely we select the part for AM printing. Also, if the part is being made through part can be simple, but it is being made through a tortuous or very exhaustive process route like multiple welding or brazing and all that thing. Those parts also we are looking for to be printed through AM. And even some brackets which are simple, but multiple settings are there, and the topology optimization can save the weight. Yes, we do. We are looking for such parts to be printed through AM, and assemblies which can be simplified and can be converted to a single component, or at least number of parts can be reduced, are also of interest. Yeah.
Okay. So good to know that you are not just taking the technical challenges, but the supply chain and operational challenges as well while screening the parts, rather than just focusing on the technical aspects. Next question I have for Mr. Anand. You being a veteran of the Indian AM ecosystem, I would like to ask you, what do you think are the challenges specific to the Indian aerospace industry for adoption of AM?
Yeah, Arpit, I would like to start with the very high level thing. The first challenge is there is no policy drafted for the adoption of AM on the aeronautic side. Typically, because we see there is a lot of activity in different companies in small areas, but from a from a complete guideline or from a policy, there's no such policy in India. I mean, typically right now, on a positive side, if I have to look at it, the Semilac is working on a draft policy to push the AM into the mainstream. But this possibly, we could take time. So from a technical challenge, I think this is probably the first one, because without a proper guideline, proper policy of adoption, AM will be going around in circles in India. So second is from not from a technical, from a government perspective. I've been looking into the different policies across the world, and if you see in the US, for example, I think for R&D work under new technologies, they have a tax credit between 4 to 7%. So, for example, Lockheed got some of those options. So, I think also from a government perspective, they should try to encourage with some benefits for adoption of such technologies. So this probably would form a very high level challenge to start looking at. The second possibility is there's always a lack of test results or test facilities, because if you want to adapt AM, you need to have a lot of data. For example, there was a question asked to us sometime back by a company, what is the Young's modulus at a certain height elevation, high altitude testing results? We don't have them. So, and I know that it's possibly not sort of available everywhere, but I think we also lack a lot of test facilities, and this potentially means that if somebody has to adapt AM, possibly the adaptation cost is going to be higher. So, I mean, this challenge of test facilities again is not only in AM, but I also see them in the medical side, for example. So if we want to adapt a new technology, we need to have a policy, and then a proper test facility, without which, it's going to be a longer cycle for people or companies to adapt them. Then the another important point which I've seen is India, if you want to adapt AM, you have to be a design owner. So when I look around, apart from ISRO, NAL, ADA, or possibly to GTRE for some extent, most of the other manufacturers in the supply chain are doing contract manufacturing. And so if you're not a design owner, many times the challenges are you don't get to change anything, a new manufacturing process. And we have sort of gone into the more reactive mode of business cycle in aerospace, because it's also possible, like for example, you could actively also be considered, like for example, if you want to change from a manufacturing process A to a manufacturing process B. I realized that recently we were working on a project, and if this is an interior of an aircraft, and if you have the ESA certification of 21J or 21G, then you potentially have the possibility to convert the manufacturing process from, let's say, thermoforming to 3D printing in polymer or whatever it is. So I think we know that we are not having too many design owners, but the contract manufacturing supply chain could possibly potentially be more proactive in trying to experiment these things, because without experiments we cannot be self-reliant. I mean, there's been a lot of talk from the government that we have to be self-reliant, do a lot of things inside India, but unless we have a policy, the testing facilities, and the design owners or the supply chain getting into these proactive mode, the challenges would remain there for many years. And last, I would also like to focus on the material side of it, because this is a very important aspect of it, because a lot of questions are asked about I mean, I do agree that changing when you start early in the development stage of aircraft project, then you have a possibility to influence the current materials. But we've been working on some projects for replacements, where we found that the OEMs have their own composition of these materials. And specifically, when we are working on our special project right now against a Russian material, so the first challenge was to really prove the GOST standards from the Russian materials to an equivalent ISO certified material, or ASM material standards. So typically, this similarities again has to be established. So the process becomes a little bit longer. Apart from all these things, for example, without these testings, we were given a component from a ghost material to be converted into ISO, and this was a non-critical part, and it's a part in the landing system. And the current replacement part made locally could not clear more than 10 landings. So we were given a target of at least 50 landings, and we were able to. I mean, though there were no results, they were willing to test them, and I'm quite happy to say that this more than 50 landings have been done on this aircraft. It's a military aircraft again. So I think a lot of emphasis has to be stressed on the policy, testing facilities, and then the contract supply chain, manufacturer supply chain should rise up and punch above and say that they probably would be able to not only follow these contracted things but also be able to develop things and get these type of certifications which are needed. And of course, materials again plays an important role, variety of materials, because when OEMs have their own composition, then there will be some variants there. Again, this has to be tested, and a lot of test results has to be manufactured. So I think these, for me, are the fundamental challenges which we would face. Apart from whatever the system throughput or whatever we're talking about, this forms the basic challenge from an Indian perspective.
Thank you, Mr. Anand, for sharing that we need a pretty coherent and holistic approach if we need to push AM in the aerospace sector in India. Uh, so we will take few more questions with our panelists today. But before that, I would request Sankha to please share the poll results that we had done in the earlier to get the perspective from our attendees as well.
Am I audible?
Yes.
So I'll be sharing my poll results right now. Just hold on a second. Is my screen visible? Hello?
Hello.
Is my screen visible?
No.
Yes, it's visible.
Yes. So these are the poll results. Hello.
So we have a pretty good perspective from our attendees, where uh, they have said that structural parts using topology optimization would be the major area where AM would get into the aerospace industry. And then obviously engine parts, interior parts, and UAV, as our panelists suggested. And in terms of hindrance of AM in the aerospace sector, we have a pretty mixed result, but certification validation, as our panelists also explained in detail, uh, is a major concern. And in terms of important attributes for the application is that everybody is looking for better quality and a faster turnaround. So that is a pretty good view that we get from our attendees. So I'll move to Mr. Godfrey and go ahead with one question to him. So now we have seen the poll results. I would uh, ask Dr. Godfrey, in terms of global perspective, apart from the flying parts, what all other applications do you think would be the potential candidates for AIM, apart from the much talked about flying parts? Uh, Dr. Godfrey?
Okay, there I am. Okay, I am officially unmuted now. So what kind of parts are applicable for additive? And let's talk. All right, that's an open, that's a pretty wide discussion. So for example, today, companies like Lockheed Martin and Northrop Grumman are 3D printing wing spars. And wing spars is the structure that goes inside the wings on your aircraft. And the reason they're doing that is because it takes well over a year to get a 20-foot long forged Ti 6.4 bar. But you can print it using DED technology. All right, so when I want to take your question and I want to run it through a funnel. When you're looking at DED's technology, large objects are being printed all the time. Companies like RPM, Sayaki, and then there's one or two in Germany. I can't think of their name right now. Godfrey. They're printing aerospace parts, but you print them very, very large. You maybe a half an inch. I'm gonna say 12 millimeters larger than you normally than what the print calls out, and then you stress relieve it and machine it to size. That is a lot faster than buying a 4 or 5 ton chunk of titanium and machining 95% of it away. So things like that are printed every day. Rotating parts are the hardest because they induce the most risk. Then, even though we do see low pressure turbine blades being printed by General Electric, because the rotation of those blades is much less RPM than, say, high pressure turbine blades. But if you go into space, SpaceX and Blue Origin, they're 3D printing everything they can, simply because they don't have confidence in the supply chain, and they're constantly changing designs. So it's very difficult to tool up. If you look at the market where you have the Honeywells, the GEs, the Pratt & Whitneys, the Snecmas, the Rolls-Royces, components that do not rotate, line replaceable units, oil pumps, valve bodies, particularly valve bodies. What else were we printing? Tubes. Tubes are simple to do. They're very low risk. Air tubes. Once you do one tube and you qualify it, it's easy to get other tubes approved. And I would say, that's the question you asked is pretty broad, but if in the engine business, it's tubes and valve bodies and line replaceable units. In space, it's everything. In the Boeings, the Lockheeds, the Northrop Grummans, the Airbuses, it's DED technology is kind of what they're pushing.
Okay. So that is a pretty good perspective on the actual parts which are being converted into AM production parts. Dr. Govind, based on your actual experience uh, in speeding and converting conventional parts into AM parts, I would like to ask, what are the specific conventional machining processes that you feel can be substituted by AM?
Yeah, but see, I feel that AM is not there to replace any conventional processes. In fact, AM will carve its own market share. And, part selection, as I told earlier, will depend on the complexity, the time it takes, the material wastage. In addition to these, there are two more strong areas where I feel AM can definitely make a dent. Is when designers start designing structures using lattice design or bionic designs, or topology optimization starts taking place widely, then there will be components which will be printed only through AM, and AM will be a supply chain for those components. In addition to that, there are some materials which we as a metallurgist knew have huge potential in terms of properties and weight and all, but we were not able to process it into components using conventional processes. And here I see AM playing a big role. Recently, we have seen that copper chromium niobium was used in making thrust chamber, and it was successfully tested. This material was known to us from decades, but we could not make any thrust chamber using this material because the conventional processes were not supporting it. And such many materials are there where AM can definitely play a big role. So, and I strongly believe that AM will carve its own market share. It is not there to replace any conventional processes.
I absolutely agree.
I agree.
That be a good supporting technology, as Dr. Godfrey also is agreeing with this. Uh, I have one question for Mr. Anand, being the business, from the business point of view. Uh, I wanted to ask, what are the new business models and collaborative approaches that AM machine OEMs can offer to accelerate the growth of AM in the aerospace industry?
Arpit, if you look at it, I try to understand the question. What you're saying is, what sort of support is provided to the industries to uh, adapt AM? Am I right?
Yes, yes. New approaches that the OEMs are trying to bring in
Okay.
to the table so that the adoption becomes faster.
Okay. So for me, I like to break this into two segments. One is if for companies to adapt AM, two things are very important. One is the knowledge, one is the availability of the technology. So when I talk about, let me first focus on the knowledge part, because AM in production is a new subject. So the amount of knowledge out in the market is limited. So to address first the knowledge gap, companies like us, we provide a lot of consulting support to people, even to think whether they should get into AM. For example, Dr. Govind also mentioned looking at the right parts. For example, the first step in consulting in the knowledge domain is to evaluate the right AM parts for them. I mean, what we always call it part selection and developing a business case. because without a business case, definitely there is no way forward, whether you're a service provider or an OEM. So typically that's the first step which we help people to do. The second part in the knowledge journey is what it takes to enter into AM. Maybe you have a business case, but now you need the right infrastructure, right people, all the complete team, because maybe the team which was doing something else might not be the right team for AM, because AM needs uh, it's just the opposite of subtractive. So you need also a team to think very differently. So that's the second step which we do. Third is definitely again on the knowledge journey becomes the advanced topics like how do you do topology optimization, what sort of value creation can you bring, what is the challenges on certification. So this is one part of the spear. So this is something, as an OEM we have to support the people, because the knowledge out there is limited. So we start with developing a business case, then providing the right team, and then giving further inputs into all the exotic topics of value creation using AM. Then we come to the availability of the tool itself or the technology itself. I think today there's quite a bit of service providers they can work with, is number one. But what we also offer is a sort of a digital journey for them. Because, okay, after learning all these things, what do? You need a sort of a digital setup. So we do support the customers in the adoption early stage by providing the consulting and the digital setup for them, and then they are always connected to what we have in India, an EOS print farm. So they could also, for all their printing, they could work with the EOS print farm at a predefined rates, and this helps them at least for the first 1 year to understand. I mean, they could come to easy conclusions whether AM is suitable for them, or they need to still go on this print farm mode, or they need an internal investment or an acquisition. So once they decide that they need something in-house, then we could work on projects like what we call they can buy it upfront, or we also work with models called boot or GOCO. Boot means build, own, operate, and transfer. So for companies, we would come and set up the facility in-house, so it's not capex for them. And then we could run this facility for a defined period. Let's say 3 years usually is what is agreed. So it will be an OPEX sort of a model for them. And then the risks are less for the people who are getting into this boot model, because they not only have the system in-house, without a capex, but they also have the knowledge of the EOS team and its eco partners inside their organization, and they are developing the parts for the next 3 years along with them. So they're not only developing parts but also imparting knowledge as they go along the journey. So options like boot, and then there is something called GOCO, whereas the company invests but they don't have manpower, so we probably provide the manpower to support it to them. And then also options like rent, lease is also possible. So both sides of the spear, the knowledge side as well as the availability towards the having this technology and the tool, both digital as well as the complete hardware setup is being promoted in this way.
That is good to know that the OEMs are coming up with innovative offerings in terms of consulting and actual building up a business case and a capex case as well for including AM into the current technology, into the current sectors. So we are almost up with time. So I apologize. We cannot discuss the attendee questions with our panelists today. So I would thank everyone for staying with us through this session. We have had over uh, 150 people joining in today, and I hope you have grasped some, if not a lot, from the session. This wouldn't have been possible without you. I would like to especially thank Mr. Godfrey, Mr. Bajargan, and Mr. Anand for uh, their invaluable inputs. It has been enlightening for all of us, getting to know more about the industry. Thank you, all the panelists. Thank you so much. Lastly, it goes without saying that the success of these sessions goes to 3dprint.com, which is one of the biggest 3D printing knowledge website in the world. TACMA India, which is the Tool and Gauge Manufacturers Association of India, having a big network, and our student partner ASME Delhi chapter, which have helped us to collaborate our efforts with their partnerships. It is because of you we have been able to spread the value of 3D printing, additive manufacturing, and its power to the next industrial to be the next industrial revolution. We will be sending you all the webinar bundle by next week, which will contain all the sessions, recordings, reports, Q&A, and much more. Do check your inboxes for all the details. Moreover, you can reach out to me, Arpit Sahu, via mail or phone call. Me and my team will be more than happy to answer any of your doubts regarding additive manufacturing. Thank you so much for giving your time. Thank you so much.
Thank you. Thank you.
Now with this, we close the web.
Thank you very much.
Thank you. Thank you. I would request all our panelists to, if they can give a small closing statement, starting with Dr. Godfrey.
Thank you. Well, first of all, thank you for inviting me to this conference. It's an honor to address the industry across India. I have many, many good friends in Bangalore area, and so it was a real pleasure to do this. I could not agree more. I could not agree more with my co-panelists. They brought up some very accurate perspectives. There's going to be a lot of questions from the panelists. If you have specific questions for me, just connect on LinkedIn, send me a question. Obviously, your first contact should be Objectify, but I'm more than willing to address questions if you have it that way. I look forward to my next trip to Bangalore, and maybe meeting some of you face to face.
Thank you so much, Dr. Godfrey. I would request Dr. Govind to please give us some closing lines.
Thank you, Arpit. Thank you for the opportunity. And I strongly believe that this AM is really going to revolutionize the design and will contribute immensely in aerospace sector. Not only aerospace, medical, definitely medical also. It will contributing hugely. And it was really nice to interact. And I once again thank you, Arpit. With that, probably
Thank you.
I'd like to.
Thank you so much. Thank you so much. I think Mr. Anand is offline. So thank you all the attendees for attending the webinar, and I request you to please go through the content, and for any queries, please connect with us. Thank you so much. Thank you.